You know, inside pretty much every single device you own, your phone, your laptop, even your gaming console, there's a central processing unit, or CPU. It's the brain of the whole operation. But have you ever stopped to wonder how this tiny, ridiculously complex brain actually thinks? Well, let's crack open the case and find out what really makes it tick. To really get to the heart of what all CPUs have in common, we're going to do something kind of cool. We're going to compare two processors from completely different eras. We're basically on a mission here to find that common thread, that shared DNA that links the ancient past of computing to the super powerful present. So, meet our first chip, the 6502. This was the heart and soul of the 1983 Apple IE, and with just over 4,000 transistors, this little engine powered a whole generation of classic computers and consoles. I'm talking the original Nintendo, the Commodore 64. It was a true pioneer. Okay, now let's jump forward about 4 decades to the M1 processor in a modern MacBook Pro. Now, this isn't just an upgrade, it's practically a different species. We're talking 16 billion transistors. That's the kind of insane power you need to build the massive, realistic 3D worlds we see in today's games. The leap is just staggering. So here's the big mystery, right? One chip has a few thousand transistors, the other has 16 billion. And yet, I'm telling you they share a common technological DNA. The basic, fundamental way they work is almost identical. So how is that even possible? What is this hidden link between them? That's what we're about to solve. To get our heads around this, we need a good analogy. So for a minute, just forget all about transistors and circuits. I want you to imagine the inside of a computer as this giant library, complete with a very special, very fast robotic librarian. Okay, so first up, we have the bookshelves. Think of this as your computer's long-term storage. It's solid-state drive, or SSD. Every single program, every file, every photo you've saved is like a book on these shelves, just sitting there, waiting to be picked up. Next, we've got the cart. This cart represents your computer's short-term working memory, or DRAM. See, you can't work directly from the shelves. That'd be way too slow. So the cart brings a few essential books over to your workspace. It's incredibly fast, but it can only hold whatever you're using right this second. And where is that workspace? Well, that's the desk. The desk is the CPU itself. This is the main hub, the command center, where all the real work actually gets done. It's where the books from the cart are finally opened up and read. Now, on the desk, there's a single sheet of paper. This represents the registers. They're these super fast, but very tiny memory spots right inside the CPU. They're basically a little scratch pad for jotting down the exact numbers you're dealing with at this very moment. We also have a simple little calculator on the desk. This is the Arithmetic Logic Unit, or ALU for short. It's the number cruncher. Now, it can't do fancy calculus or anything, but it is unbelievably fast at basic stuff like adding, subtracting, or just comparing two numbers to see which one's bigger. And finally, the most important part of our whole library, the robot. This is the control unit. It's this tireless librarian that reads the instructions from the books, moves data between the paper and the calculator, and basically coordinates everything. It directs all the traffic. It's the boss. All right, so we've met all the players, we've got the library, the desk, and our amazing robot librarian. Now let's actually see what happens when we give this robot a job to do, when we run a program. So, what even is a program in our library analogy? Well, it's really simple. It's just a book of instructions. Think of it like a recipe. Each instruction is a simple, numbered step, and the data, the numbers, are the ingredients the robot is going to use for that recipe. Let's watch the robot run a tiny little program. First, an instruction tells it to load a number from a book and write it on its sheet of paper. Easy enough. Next, the increment instruction tells it to take that number, pop it into the calculator, and just add 1. Finally, the store instruction tells it to take that new result and write it back into the book. Simple, right? But wait, how does the robot know which step of the recipe to do next? Well, it uses a special little spot on its paper called the program counter. After it finishes instruction number 1, the counter just ticks up to 2. Then after 2, it ticks up to 3, and so on. It just follows the recipe one step at a time, perfectly in order. Now this simple, repetitive process we just watched, the robot grabbing an instruction and then doing what it says, this isn't just a part of the story. This is the story. This is the secret technological DNA we've been hunting for this whole time. Think about it. The robot's 3 basic actions. finding the next step in the recipe, figuring out what that step means, and then actually doing it. That simple loop is the fundamental principle that drives every single CPU ever made, from the oldest to the newest. And this brings us to the absolute core of it all. This process has a name. It's called the fetch, decode, execute cycle. The robot, the CPU, fetches the next instruction using its program counter. It decodes that instruction to understand what to do, and then it executes it using the calculator or moving data around. And then it just repeats over and over and over. And this brings us full circle. Remember our two chips? That old 6502 chip from 1983 could run this fetch, decode, execute cycle about 1,000,000 times a second. Pretty fast, right? Well, the modern M1 chip does the exact same cycle, but it runs it over 3 billion times a second. The fundamental DNA is identical. The only difference is the blistering, almost unimaginable speed. And there you have it. This brilliantly illustrates our main point. This simple three-step loop is the universal constant in computing. I mean, from running a simple game on an Apple IIe to training advanced AI in a massive data center, it's all powered by this exact same fundamental cycle. It truly is the heartbeat of our digital world. So when you really get down to it, every piece of software you have ever used, every app, every game, every website, is just a very, very long recipe. And it's being followed by a robot completing this simple loop billions of times every second. We've uncovered the fundamental engine of our entire digital world. So the only real question left is, what amazing new recipes are we going to write for it next?